So, circular motion, some of the key ideas we're talking about here. What I want to talk about first is the written section. So what are you going to see on the written section? There's 4 or 5 written. I can't remember. And of the 4 or 5 written, 1 is on Earth and the other remaining are in outer space. So one is, and we'll talk about that, looking at either roller coaster, amusement park ride, Ferris wheel, car going around a corner, or Gravitron, I'm trying to remember. But let's talk about space. First of all, given R or T or V orbit, you should be able to find R or T or V, or heck, big M for that matter, or little m. No, little m you can't because it cancels. But given any of these, you should be able to find any of these. Now, the key idea, what's the key trigger word? Orbit. If you're not in orbit, you can't go gravity equals centripetal. So, as an example, a satellite is orbiting the Earth with a period of, let's make it, oh heck, ISS orbits roughly every 100 minutes, which is 600 seconds. Let's go 1,850 seconds. Oh, you know what? Let's make it more realistic. Let's make it every 8.5 hours, so we have to do a unit conversion. What is its orbital radius? What is its orbital speed? Key idea, orbit. So, what have I said to you folks? When you see that we are in orbit, what can we write? There's a little one-line idea. Gravity is what's pulling me around in a circle. Gravity, Anthony, won't change. It's always going to be big G, big M, little m over r squared. Centripetal force is always MAC, but you then, don't forget the M, by the way. One of the common mistakes kids forget to write mass times acceleration because, Jake, the acceleration has all sorts of variables in it, so they think, oh, that's the force, and then the M doesn't cancel, and they freak out, or M doesn't cancel, and they leave it in, and their answer is now off. But little m times AC, the question is which variation of A depends. Depends on whether they ask for or give you speed, or ask for or give you period. And since they gave me the period, I'll use that one, which is 4 pi squared r over t squared. Is that okay so far, Rach? The period is 8.5 hours. I need to change that to seconds. How many seconds in an hour? In Physics 11, most of you had this on your fingertips, but you've forgotten. I think it's 3,600, right? It's 60 minutes, 60 seconds. So can someone on their calculator go 8.5 times 3,600?
If you were really good, Mr. Dueck, you could do it in your head.
Yeah, I'm tired. What is it? 30,600 seconds. Just to put that in perspective, the ISS, which is in low Earth orbit, barely above the Earth's atmosphere, orbits every 96 minutes, so every hour and a half. So this is going to be considerably higher than the ISS. I like you in the front row. This is a better place to learn. Ty, can I do that? Yeah. Does an R cancel here? Not in this one, because remember, stuff moves diagonally. As a matter of fact, I think I'm going to get an R cubed when I move that up there. An R cancels if it's the V squared over R, because you have R's in the bottom. Okay, what do they want me to find? Well, we'll call this part A, we'll call this part B. So it wants me to find its orbital radius. We will get the r by itself. So I think when I do that, this is going to move to there, this is going to move to there, and this is going to move to the bottom. I think I'll get this. R cubed equals big G, big M, t squared over 4 pi squared. And, holy smokes, it is useful how to get rid of a cubed. Cube root. Okay. Do I need to go further, or are you guys okay if we plug and chug the numbers and we're good? Okay? So that's part A. I won't bother solving it. You can try that if you really want the practice. Part B, well, I would start out the same way, but I would say big G, big M, little m over r squared equals, oh, wait a minute, Mr. Dueck. If I go mv squared over r, so for part B, I could take my answer for r and I could plug it in there and then I can solve for v. We've seen this one before. V orb was big G, big M over r square rooted. That would work. Or if you wanted to, you could actually say AC has to equal AC. 4 pi squared r. You know what? I'm going to take that back because you need to use r no matter what, so I would use this. I was going to say you could use the period to find v, but really you can't exactly, not without the radius. Is that okay, Mac? Satellite is orbiting planet of mass, oh heck, of radius, with, how do I want to do this? At an orbital radius of 6.7 times 10 to the 7th power, and then I go, don't need to write power, Mr. Dueck. This is what happens when I type in a hurry. Yay! But I do need to put meters. If the satellite has an orbital speed of 8,500 meters per second, what is the mass of the planet? So here's the little twist as well. We are in orbit. What am I asking you to find this time, Darian? You haven't given one like this. Well, are we in orbit? So what can I write first? Gravity is what's pulling me in a circle. I think I gave you enough information. I think we'll be good. Big G, big M, little m over r squared equals mv squared over r. Darian, again, that cancels. And one of these cancels. Darian, what did you say they wanted us to find? Oh, let's get the big M by itself. I think it's going to be times by r. You know what? I think M is going to be v squared. R. Did they give me the orbital speed? Did they give me the orbital radius? Big G is 6.6. You know what? Okay, I can do this too. Fair enough. In other words, what I'm saying is if you're in orbit, I can ask you to solve for a lot of stuff as long as I give you the information. Or I could have given you the period instead of the orbital speed. You would have just put the 4 pi squared r over t squared version here, but still been fine. So orbits, note, read the question carefully. Make sure they give you or ask for a radius, not an altitude. If they give you an altitude, add the radius of the planet. Or if they want an altitude, you're finding the radius, subtract the radius of the planet, and that tells you how far from the surface. Is that okay, Kyle? All right. Second key concept. Gravitational field strength. Example. Suppose a satellite is in orbit where the gravitational field strength is 7.5 newtons per kilogram. What is its orbital speed? And I guess I should say is in orbit about the Earth. Okay, what did they give me this time? Did they give me the radius? Did they give me the period? Did they give me the speed? They want the speed. What did they give me? Okay. They gave me the gravitational field strength, our symbol for which is little g. What's the gravitational field strength on the Earth? 9.8 units, either meters per second squared or newtons per kilogram, because what you're saying is on the Earth, every kilogram, yep.
Does this say above or about?
Above or about? Is an orbit about the Earth or above the Earth? You could be in orbit about a planet. Works grammatically, I think. Above also works. Yep. Gravitational field strength is measured in meters per second squared or newtons per kilogram, because it's saying every kilogram of mass feels 9.8 newtons tugging it down on the Earth's surface. Are we on the Earth's surface? How do I know we're not? Well, the gravitational field strength is smaller, is less. We must be up there somewhere. What's the equation for G, for gravitational field strength? Not on your formula sheet. It comes from this idea that gravity equals gravity. On the Earth, we calculate gravity as mg. In the universe, we calculate gravity as big G, big M, little m over r squared. And if you know that and realize little m cancels, that, not on your formula sheet, that's the equation for gravitational field strength. So in this question, they've told me that it's 7.5. What can I find from that? I can find my orbital radius. R is going to be big G, big M over 7.5, whatever. How does that help me? Well, now that I have R, now I can go gravity is pulling me in a circle, and I can get V orb. I think it was big square root, big G, big M over R, and I could find that by plugging it in there. So please don't forget, I guarantee on the multiple choice section, not on the written, there's going to be a question or two about gravitational field strength. It may be as simple, Rachel, as me telling you your radius and the mass of the planet and saying, tell me you know what, I could make up a planet. I could say planet Lee has a mass of 9.2 times 10 to the 25th. And a radius of 6.3 times 10 to the 8th, what would the gravitational field strength be on its surface? You could crunch the numbers. Oh, it's got a gravitational field strength of 12.6. So you'd feel heavier on that planet. Or it could be somewhere around the Earth in orbit or somewhere around the moon in orbit. Oh, please read the questions carefully as well. Make sure there is one question, just for giggles, I'm putting you around the moon. I'll try and remind you when I go through the test with you, but it's on the written. Read carefully. If it just says orbit and no planet, probably you can assume we're the Earth, unless the question is saying find the mass of the planet. Wouldn't be the Earth because that's on your formula sheet. So make sure you're okay with gravitational field strength. Then, also energy in particular, how much work? And there's two concepts here. To lift the satellite, to put in a stable orbit, which is the second idea. So let me give you an example of both. How much work would it take to lift a 3,650, 2,650, because that's what apparently I hit, kilogram satellite to an altitude, Mr. Dueck, to an altitude of 7.5 times 10 to the 6th meters above the Earth? So here's the key idea, Mickey. Does this question, Rachel, mention orbit? In fact, the key word, life, can't even type, no wonder you're confused. Lift, the key word, if I typed it correctly, is that. What we're imagining is you're just lifting it up, straight up with rockets, and as soon as the rocket finishes, it's going to come crashing back down to the Earth. What's this question asking me to find? So, here, except, are we in orbit, Anthony? So, if we're not in orbit, we're going to assume that we begin and end at rest, and we can cross out the change in kinetic. Now, if you're in orbit, Rob, you can't cross out the change in kinetic. In fact, in orbit, what we've said, Cole, you must have kinetic energy to stay in orbit because you're moving sideways at exactly the right speed so that you're free falling to the Earth but never getting any closer. And I'm going to give you one of each of these. What's change in anything? Final minus initial. Are we cosmic or am I using MGH? Cosmic. Now, this would be just to lift it up, and we would then say final minus initial, but rather than solve this, what if instead it gave me exactly the same question? Well, you know what? No, let's do this. So, let's write. Change in potential is going to be negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. This is going to be a fairly long question. Negative 6.67 times 10 to the negative 11. Are we Earth? Yay. 5.98 times 10 to the 24th. Does the mass cancel out here? No, it takes more fuel to get a bigger satellite up there, so the 2650 doesn't cancel. Our final is going to be our final orbital radius. Now, they didn't give me my final orbital radius. Instead, they gave me an altitude. Sorry, attitude is what I get from you guys. Altitude is what the question gave me. So, you like that joke? That was new. Okay, is that a hand up, Grant, or are you just stretching? You're just stretching? Okay. What's my final orbital radius? Well, it's going to be the radius of the Earth plus my distance above the Earth. That's going to be my final potential energy. It is going to be negative. What's a minus minus the same as, Kyle? Okay. And then it's going to be same number, all over. My initial is the surface of the Earth. And I do that on purpose, both to save writing, but to say to you guys, here's how I'm going to type it on my calculator. I'm going to type the first term very carefully. Holler if I make a mistake, because I'm typing in a hurry. Did I type that right? I think so. I'll carry it to like 5 sig figs, because I'm going to use this. Negative 7.6152 times 10 to the 10th plus, and then I'll just backspace and edit. I delete that. Hopefully by now there's no poor schmuck in here who doesn't have a calculator that lets them backspace and edit. If you do, I laugh at you. Positive 1.6567 times 10 to the 11th. So my change in potential energy is going to be that number, take away, or plus negative, 7.6152 times 10. I mean, you can try typing that whole thing in one fell swoop. I really wouldn't advise it, Jake. And you get a change in potential energy of 8.952 times 8. B. What if, how much work to put this satellite in a stable orbit? We'll do the same question, but put it in orbit. What's this question you want me to find, Jake? How much what? And work is what? Change in potential plus change in kinetic. We just found the change in potential, thankfully, so I'm just going to make a little note here. Change in potential equals 8.952 times 10 to the 10th joules. But we are in orbit, and so because I'm in orbit, Ryan, kinetic energy can't cancel out. What's change in anything? Let's find the change in kinetic. So the change in kinetic is going to be KE final minus KE initial. And we're going to assume that we start from rest. There's a couple of shortcuts here that you can survive, Rob, just fine without. But I'm going to point them out to you. You may recall that I told you that there was a relationship between your potential energy in orbit and your kinetic energy in orbit. Do you remember? And I said you could survive without memorizing it. It was just kind of nerdly cool. Anybody remember? Yeah. Close. So the kinetic is half the potential, but positive. The total is half the potential, but still negative. So for what it's worth, if I was really wanting to be quick, and I don't know if I would do it this way, I could say, hey, here's the final potential. You know what the final kinetic should be? What are you pointing at? It's right there. I could divide that by 2 and make it. I'm willing to bet if I crunch the final kinetic, I think it's going to be 7.6152, scientific notation button. I bet you it'll be that. And I could now just go to it. I'm uncertain, I'm uncomfortable, I'm unsure enough about that little tidbit of trivia that I often just go with it the long way. So hey, what is kinetic energy? What's it been since Physics 11? So final is going to be a half mv final squared. In fact, v orbit squared. Did they give me v orbit? Nope, they gave me the altitude. Wait a minute, I can find the orbital speed because we're in orbit. I can say,
Hey, gravity is what's pulling me in a circle.
and I think we ended up with v orbit equaling the square root of big M, big G over R. Oh, wait a minute, though. You know what? Since I want v squared, why don't I get really clever and just say that? And now, that's big M. Hey, wait. See what I wrote there? See what I wrote there? This is our final, yes? Big G, big M, little m over R final, half of that. Big G, big M, little m over R final, just negative. You know what? I am convincing myself. Although now, if I got this far, Rachel, I probably would just plug and chug. But I'll bet you we're going to get really, really close to, but not be exact because we've rounded off, really close to this. Let's see. It's going to be 0.5 times 2650 times mass of the Earth, 5.98, 5 point, whoop, come on, 0.98 times 10 to the 24th times 6.67 times 10 to the negative 11 divided by bracket 6.38 times 10 to the 6th. The final radius was the radius of the Earth plus the altitude, 7.5 times 10 to the 6th. Ha! There it is. Look at that. 3.8076 times 3.8076 times 10 to the 10th joules. We're not done. So the total work whatever the heck that is. So that question, in fact, I think both of those are going to be on your test. I'm going from memory. I think in one question, I just asked you to calculate how much to lift it and let it fall. And then another question, I asked you how much to put it in orbit. What else? Use when there is conservation of energy. Use when there is a change in height and speed, but no work is mentioned. Example. 1,500 kilogram satellite leaves the surface of the moon at 90. You know what? I better make sure I don't accidentally make it bigger than escape velocity. 1,500 meters per second. How high will it get before falling back down? Noah, is there a change in height in this question? Is there a change in speed? I think it's going to be slowing down. Does it mention work? Okay. So, now this question that I'm doing here, I think I put something like this on the multiple choice, not on the written. It's going to be a conservation of energy. Don't quote me on that. I think it was multiple choice. KE initial plus PE initial, KE final plus PE final. If anyone has their formula sheet, I'm going to need values for the moon because those ones I don't have memorized. We would say that our final kinetic was 0 because it's going straight up and coming to a stop and then falling back down, but for a split second at the top, it's 0. Kinetic energy initial, hey, that's going to be a half mv initial squared plus negative big G, big M, little m, all over R initial. Wait a minute, Mr. Dueck, if you're starting out on the moon, can't you use MGH? We're going cosmic. We better be cosmic the whole way through. Equals negative big G, big M, little m, all over R final. Okay? What's this question asking me to find? in my variables here, in this equation, what's it asking me to find? Because there is no height in this equation. What's it asking me to find? Okay, it's asking me to find that. Now, I've said this to my classes. I don't know if I said it to every block. Mickey, what I would do, I would not try and get R final by itself. What I would do is crunch this. You have all the numbers, you have the mass, you have VI squared, negative big G, M of the moon. Make sure you use the moon. Little m they gave you in the question. R initial radius of the moon. I would get an answer that equals negative big G, big M over R final. And only now would I get R final by itself. Because really it's this answer over 1. It is, Zach, 1 fraction equals 1 fraction. You would then get R final equals negative big G, big M over whatever the heck the answer was when you cross multiply. Is that okay, Rach? Okay? Oh, by the way, you still wouldn't quite be done. This said how high. All you found is the distance from the center of the moon, and it wants the distance from the surface of the moon. I'd have to subtract the radius of the moon to get there. Okay? Or dropping an object from space, find V final. V final would be in this equation here. R initial would be whatever altitude, height, whatever radius you dropped it from. If they gave you a height, you'd have to add the planet's radius. R final would be surface of the planet. And then you would find out its impact velocity. I think we did do one like that in our notes and in our homework. That's it, I think, on the written for stuff I can do with energy. And as I said, those last two, I don't think I put on the written. I think I put something with a conservation of cosmic energy. I think I put it on the multiple choice, I'm pretty sure. But I said there was one, what? On the Earth question. Ferris wheel, roller coaster, or gravitron, right? Okay. Okay, I wanted to do this. Oh, I did do one like this where I gave you the acceleration due to gravity, and we found its speed because acceleration due to gravity is another word for gravitational field strength. So you found R, and then once you had R, you found, okay, that worked. I think there was a nice picture of a, okay, this would work. Let's see if I can find a better Ferris wheel question and just change the numbers. By the way, number 18, this is my old unit review that I used to give out before I went all digital. This is just what we did, but this is from the Earth. Here it's telling you how many joules of work you did, which is actually easier. Show me a Ferris wheel, Mr. D. Sure, this works. I'll just change the numbers. There is going to be some kind of on the Earth circular motion question on the written. It's either going to be, I'll tell you, an amusement park ride or a car going around the corner in a circle. So under amusement park rides, it's either going to be a Ferris wheel, a roller coaster, or the Gravitron. Is that okay? So I'll do a Ferris wheel. I'll talk about how you would tweak this. The only difference between a Ferris wheel and a roller coaster is the top. At the top, which way is your head pointing on a roller coaster? So which way is the normal force pointing on the roller coaster? Which way is gravity pointing at the top? Your equation, roller coaster, is winner plus winner equals what's moving you in a circle. Your equation, Ferris wheel, is winner minus loser. So it's moving, okay. 75 kilogram, the centripetal force acting on it. You know what? Let's change that. Let's say that rotating uniformly every 36 seconds with radius 24 meters. That's way too big. 14 meters. Make it a small Ferris wheel. Find Fn at the top. Okay. What are the forces acting at the top? Get the obvious one. What else? Normal force. Should I draw normal force bigger, smaller, or the same size as gravity? And how do you know? Smaller? Why? What path are we tracing out? Where must my net winning force be pointing? Toward the... So I know normal force is smaller. Compare that with the bottom, where normal force would be bigger than gravity. My equation at the top is going to be gravity minus Fn equals m. Did they give me speed or period? 4 pi squared r over t squared. Are you guys okay? You get the Fn by itself, right, Rach? Plus that over, at the same time minus that over. They gave me the mass, they gave me the radius, they gave me the period. Now it's plug and chug. At the bottom, you'd have a different equation. Either of those, to me, Rafi, would be fair game. Or a roller coaster where you would have winner plus winner, and I could say find the normal force as well. Is that okay? I think if I was clever... Yeah, sure. Gravitron. Okay. The question we did in the homework, well, I'll you know what? I'll get it set up, and then I'll say, here's what I could ask you to find. So here's the gravitron. I'm making up numbers. Suppose the radius equals 5.1 meters. Period or velocity. Well, if you have a ride like this, it's easier to measure the periods. I'll give you the period. Suppose it rotates once every 1, 2, 3. That's a little slow. Every 2.1 seconds. 1,000. That might be a bit fast, but we'll see. I think what we did in the homework was that. The key idea here, Cole, is getting the free body diagram correct and looking at what your equations are, in which case then I can give you anything and say find anything else. So, what are the forces acting on this person? Get the obvious one. Are we on the Earth? So we can use good old mg. And I should have said that with the Ferris wheel as well. Is this person sliding down the wall? Are they sliding up the wall? So I think it's reasonable to assume there's an equally sized force that way. Which one? You may remember, but I'll derive this just in case. Oh, what path is this person tracing out? So there has to be a net force also pointing in. Why would this be wrong? What never goes on the free body diagram? FC. Okay? And I'll try and trick you on the multiple choice. Absolutely, I'll be giving you one multiple choice question where I give you several free body diagrams to pick from, and I'll say pick the right one. And almost always in one of them, I've put FC on the diagram as well, because it's there, but it's the vector sum. Don't pick it. What force is pushing him towards the center? So what force is pointing up? So as equations, I have this, two of them. Normal is pushing me in a circle, and since they gave me period, I used period. What's my vertical force equation? Friction equals mg, except what's another way to write friction? Friction is what times what? So, for this question here, I guess I need an expression over here. I don't know the normal force. Oh, but look. I know another way to get the normal, another way to express the normal force. I guess here, the normal force is equal to mg over mu. And I get Oh, not Fn, Mr. Dueck. Could you get the mu by itself? Okay. I'll let you take it from there. Or, to be honest, I could give you the period and mu and say find the radius. Or I could give you mu and the radius and say find the period. Or I could give you this instead of the period. I could give you the speed. And it would still be normal force equals mac, but it would be mv squared over r. Right? So those are hints for the written, and I snuck a few in for the multiple choice. I did talk about gravitational field strength, right? Okay. Also, don't forget the basics. People get so good at doing orbits and things. I have no problem giving you, what's Newton's universal law of gravitation? Big G, big M, over. Okay, I have no problem giving you FG. Solve for or little m or r. Right? Don't forget all our physics 11 stuff. So I think on the multiple choice there is a question where I give you the force of gravity. I think for an asteroid around the sun or something like that, I say it's experiencing a force of blah, 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 blah. And then I say it's the sun, so you have the mass of the sun on your big sheet. I think I say find the mass of the asteroid or the radius of the asteroid. I don't know, something like that. So don't forget that. Bear with me. I'm going to pause the video because now I need to look at my notes. My mind has gone blank for what else. For horizontal circles, also look at a car going around a corner. Just to walk you through that, we did that in lesson, hello, Mr. Dueck. Let's go block A. No, let's go block G, Mr. Dueck. We did that in lesson 2, horizontal circles. And this is where we said for a car going around a circle, I found it easier to draw the car coming out of the page towards me, a front view. This was my high-tech drawing of the car with the square tires and all that. But the key idea, what force is pushing you around a corner? Friction. So you have friction equals Fc. Mu, I don't know the normal force. Oh, but look, another force same size as the normal force. Mu mg equals either mv squared over r or m4 pi squared r over t squared. So that's fair game. And then there's one more that I need to find, Mr. Dueck. You know what? Let's go to here. Lesson 2. Something like this. I think there's going to be one of these on your test. One of these. Let me see if I can find one with different numbers. Otherwise, I'll just... Oh. Nope. This hasn't got the hanging guy. Come on, Mr. Dueck. No, apparently... Really, Mr.? Oh. I think that's the same question in your homework. I'll just change the numbers. Tutorials. Ball on string held by heavier mass. Like, what? Geez, Dueck, hitting the wrong thing. Like this. I'll change the numbers. And I think this is going to be almost a wrap-up. Then it's going to be specific questions you guys have from the review. And I will do about a 10-minute Q&A at the beginning of class as well tomorrow and Wednesday. Okay? 8.3 times 10 to the negative 3 kilogram ball is attached to a 4.2. So this is 4.2, and this is 8.3. The ball travels in a circular path of radius. I'll leave the radius the same. What's the speed of the ball? What are the forces acting on these? First of all, let's do the little black one there. What are the forces acting on it? Get the obvious ones. So I have little mg down, normal force up. What path is it tracing out? What's pulling it in a circle? Not friction. Okay. So my first equation is tension equals Fc. And since they want the speed of the ball, I think what I would say is tension equals little m, because that's the one that's moving, v squared over r. I would say v is going to be tension times r divided by little m square root. Time for me to go home. Thank you. Google knows everything about me, right? Problem here, I don't know tension. Or do I? Hey, there's another mass. Let's write a free body diagram. Let's write a force diagram on this other mass. Hey, what are the forces on this big mass? Get the obvious one. Big mg. What else? Tension. And if it's not going up or down, if it's in equilibrium, what can you tell me about tension and big mg? Okay? So now you can replace it and you'll get V is going to be big M G times R over little m. Okay? On the very, very last day, the very last lesson that we did, we looked at cool stuff. And in particular, because it was cool, we did analyze the potential energy of a roller coaster. We used conservation of energy to figure out how high the hill had to be. It's cool. I'm not going to throw that on the test. If it's a roller coaster, it's just going to be, tell me either the normal force, or if I give you the normal force at the top, tell me how fast it's moving at the top, because either of if you know one, you know the other, vice versa. But I'm not going to be asking you to derive this thing, although it was pretty cool. Any questions from the review, from the unit review, where you're saying, Mr. Dueck, I've looked at your answer key. Darian, what number? Oh. So, oh, yeah. Thank you. I would have forgotten to do that. Make sure you thank Darian for reminding me. All righty. Number one, there is going to be somewhere a conceptual. You need to know this, okay? If you're moving in a circle, what direction is your acceleration? Toward the center. What direction is the net force? Toward the center. What direction is your velocity? Tangent to the radius. So I'll probably give you a question with one or two or all three of those and diagrams to pick from. In fact, I'm sure I did. Okay, because that's conceptual, but that's key concepts. So number one, the velocity would be straight up, path x. Number two is a little plug and chuggish. So number three, I told you I'm not going to put one like this on your test, although you should be able to handle it now. What was it? 2.5 times the radius was the lovely equation we ended up with, but you can derive it. Number five would be a nice Darian using principles of physics question. So what kind of using principles of physics right to explain questions can I ask? Certainly a lot of the stuff with orbits, I can say, okay, here's satellite A, here's satellite B. If satellite B has a longer period, is it higher or lower? Shorter period, is it higher or lower? Higher speed, is it higher or lower? If it's higher, is its speed faster or slower? If it's higher, is its period faster or slow? All of those, you can get the appropriate variable by itself and look at how the variable that they gave you affects your new answer, right? And I think there's a bunch like that in the homework. 7 is good. 8 is good. Explain what? It's a car. It's moving you in a circle. This is what we talked about. Here's the front view. What force is pushing you in a circle? Friction. Okay? So friction is what's pushing you in a circle, and they want the minimum coefficient of friction, so get the mu. Oh, I don't know the normal force. Look, and another force same size as the normal force. Is that okay?
Okay, but what is horizontal?
Horizontal, flat. Vertical, up and down. Horizontal, flat. So a horizontal curve. Sorry?
So is the force of friction?
That's what's pushing you in a circle. Yeah, it's like this. Picture here. Oh, there it was. Okay. What we're saying then is, here's the car coming towards you. Friction is what's pushing you in a horizontal circle. Is that okay? So I like number 8. 10 is cool. Not as a written, but it's kind of a neat multiple choice question. That's a bit of a tough one. You know what? I'll take it back. I'm not going to say I like it, I like it, I like it. It is kind of cool, though. Turns out when you're swinging in a rope swing, the maximum tension at the bottom is exactly 3 times mg. Which, you may notice, you've had me for a couple years, I have a fondness for something ugly that ends up being a lovely clean answer, like the roller coaster question in lesson 8 as well. Anyways, 12 is good. I like number 12. I like number 12. 13, I like number 13. I like number 13. 14, I told you I'm going to ask you something about accelerations and forces and velocities. 16, I like number 16. I like number 16. I wrote here, don't need to find the bottom, because once you found the top, there was only one answer that had the right force for the top. So although the bottom ended up being 590, once I had the 430, I quit, because that was the only possible correct answer. I'm teaching you my chart method of crossing and checking, right? Okay, the conical pendulum, not on your test. We really look at this situation more in equilibrium, and I've moved equilibrium, if we get to it, to the very end of this course. So don't worry. You can try those, but don't worry about them. I like number 19. I like number 19, finding a gravitational field strength. And then 19b, you get to do something with it. That's kind of cool. I like number 22. I like number 22. I like number 22. Stunt plane, that's really the same physics as a roller coaster or a Ferris wheel, right? Draw a good free body diagram. I like 23. 23 is nice. 24, here's an example where I'm giving you the gravitational force, 228 newtons, and I'm saying find something else, in this case, little m. Okay. 26, definitely. How much work? In number 26, it's lifted, so are we in orbit? So that's why there's no change in kinetic. 27, I told you I like rides, so either this one or roller coasters are fair game. Uh, 31, because in particular, finding the orbital speed, sure, totally. And there's a good example of a using principles of physics right to explain question. 33, 33, 33. '36, I'm giving you the period and saying find the radius. Sure. Oh, because this is the one where you cube root, which is kind of cool. 37, Darian, is an example of a nasty with gravitational field strength. So they gave me the acceleration due to gravity. It's nearly 0, so I know we're really high. I can use that to find the orbital radius. by using little g equals big G, big M over r squared. And once I have the orbital radius, I can find V, and then I can find kinetic energy. I don't know if I give you a 3-step one like this, where then also I said find the kinetic energy. I would have no problem giving you the gravitational field strength and saying find the speed or the period. First, find the radius. Okay. Number 38, here is an example of finding gravitational field strength. And so here, because remember, gravitational field strength is the same as acceleration due to gravity. So I said it's dropped. I can find near the surface. Mars has a little g of 3.75. And so I said that also has to equal big G, big M over r squared. We can now solve for the mass of Mars. In fact, I think in our notes we solved for the mass of Earth this way, and we said it turned out Earth was heavier than we thought. That's how we suspect, or we first suspected there was a dense, heavy iron core at the center of Earth, that it wasn't rocks all the way down. Uh, 41, Ferris wheel, sure. 42, here's a conceptual idea. Work is the area under a force versus distance graph. 43, absolutely. 44, I told you, multiple choice concepts. Which way are you accelerating? Which way is your force? Which way is your velocity? By the way, I don't think I like 47, but remember, it's asking you to find the slope. So I said, when in doubt, the slope is the rise over the run. So I said the slope was FC over V squared. I said, hey, I've got an equation that happens to have F and V squared in it. It's this one. So when I wrote rise over run, I said, I guess the slope is the mass divided by the radius. It's got to be. I'd never seen that before, but it's got to be. Rise over run. So those graphing tricks that I gave you really work. Sure, 49. Here, find V and then find kinetic energy. So an extra step. I'll be honest, to me, 50 shouldn't be a scholarship anymore. It used to be. But certainly if I let this be on the Earth, and instead of saying find the height, if I said find the radius, that would be fair game. It's the extra step of having to be on the moon, and then the height is your final radius minus the radius of the moon. Fine. 51 is cool, but not on your test. But I think I'm going to add 51 to the lesson next year. It's just nerd component. See, to me, 52 is now sort of fair game, although, again, it's a height question. Uh, 53, no, although it's kind of cool. 54, no, although it's really cool. 55, no. So the scholarships, if you're trying to get 99s and 100s, you should try the scholarships. Those of you that aren't trying to get the 99s and 100s, you should at least look at my answer key. You should be able to follow my explanation for the scholarships, I hope. Any other questions? Reminder, I've put my previous 4 tutorials on the website. If you look under Block A or Block G or Block H, they're all there. The longest one seems to be the 2010 one, and that's the one that's got 7,000 and some hits, so apparently it was well liked by the internet. I must have gone into more detail. Okay, so hang on, let me hit